So next we have is effect of substituents on the acidity of carboxylic acid. As we have already discussed that the acidity of any acid is directly proportional to the stability of its conjugate base. So if conjugate base is more stable, acid will be more acidic. So now we know that the stability of carboxylate anion is actually due to this resonance stabilized structure. So now let's try to understand what effect the substituents are going to have on the stability of this carboxylate anion. Since carboxylate anion is a negatively charged species, so we know any group that helps in dispersing this negative charge will actually increase the acidity of carboxylic acid. For example, if I put an electron withdrawing group, we know electron withdrawing group will actually pull away the electron density away from carboxylate anion, and hence it will decrease the electron density and hence will increase the stability. So that is what I have written. Electron withdrawing group increases the stability of carboxylate anion, and if anion or the conjugate base becomes more stable, its acid will become more acidic. So I can say putting an electron withdrawing group actually increases the acidity of carboxylic acid. Whereas on the other hand, if a substituted carboxylic acid is having an electron donating group, the role of electron donating group is to pump electron density onto the substrate to which they are attached. Now due to the release of electron density, what will happen is, since they are also releasing electron density and anion is already having electron density, there will be net increase of electron density, as a consequence of which electron density increases and the anion stability will decrease. Since conjugate base becomes less stable, in this case the acidity will decrease. So it decreases acidity. So if we have a substituted carboxylic acid, putting an electron withdrawing group is actually going to increase its acidity, and putting an electron donating group will decrease its acidity. Now I am going to write the order of electron withdrawing group tendency, which actually increases the acidity of carboxylic acid when they are attached as a substituent. So in this case we have a phenyl ring, then more than phenyl you have iodine, bromine, chlorine, fluorine, CN, NO2 and CF3. So if these are present as the substituent, then the acidity will be more with CF3 as a substituent compared to nitro, which will be more than CN. When CN is present as a substituent, then it will be more acidic than fluoro. So on the basis of this, I am going to write a general order of acidity which is given in your NCERT, which you should see here. So the first one, which we have already discussed, is the trifluoroacetic acid, which is one of the strongest organic acids known. If I replace fluorine with less electronegative chlorine atom, then I know its electron withdrawing power decreases a bit, as the minus I effect of CF3 will be more than that of CCl3. If I decrease the number of electron withdrawing group, let's say I make it as CHCl2, then due to the less number of chlorine group, they will have overall less electron withdrawing effect. After that you will have CH2, NO2, COH, then the next acid we are going to have will be CN, CH2, COH. After this, the one having the next higher acidity will be when it is fluorine, CH2, COH, then it's going to be bromine, CH2, COH. After this, before bromine you will have, so this will be chlorine CH2COH, Then after this you will have BrCH2COH. After this we are going to have our formic acid. After formic acid we will have Cl, CH2, CH2, COH. This will be more than our benzoic acid, which will be PH, C, double bond OH, which is going to be more than PH, CH2, COH. This will be more than CH3, COH, and which is going to be more than CH3, CH2, COH. So this is the overall order of different carboxylic acids which are given in your NCERT, which you have to understand. Now I will give you some idea for comparison, like how to compare this. For example, if I take out of them CH2, F, COH, CH2, COH, then chlorine is substituted, CH2, COH, when bromine is substituted, and CH2, COH, when iodine is substituted. So if I have to compare the acidity of this differently substituted carboxylic acid, then I know I always compare it with the stability of its conjugate base. That means the stability of its conjugate base will be the deciding factor which is going to be more acidic. So here we are having fluorine, here we are having CH2, C double bond O minus chlorine, CH2, C double bond O minus bromine, and CH2, C double bond O minus iodine. So now in this case, I know the inductive effect order or the minus I order for halogen is fluorine has the strongest minus I, then chlorine, then bromine, and then iodine. If you notice one thing, that carboxylate anion in all the cases is resonance stabilized. So that resonance stabilization is present in all of these acids. The other additional factor that we have is stabilization provided by an electron withdrawing group. So I can say since fluorine is more electronegative than chlorine, it's going to pull more electron density towards itself, due to which negative charge will be dispersed more, and dispersal of charge always leads to stability, which is the reason why when fluorine is substituted, it's going to withdraw more electron density towards it compared to when chlorine is attached. Similarly, bromine has less inductive effect, so the electron density that it is going to pull towards itself will be comparatively less than chlorine and fluorine. And iodine, it will be even less. So based on their ability to stabilize the negative charge, we can say since the dispersal of negative charge by polarization happens maximum in case when fluorine is a substituent, we can say this conjugate base stability order will be, this conjugate base is more stable than this one, this will be more stable than this one based on their electron withdrawing tendency. So as we know, acidity of an acid is directly related with the stability of its conjugate base. We can say this will be more acidic than this one, which will be more acidic than this one. So that is one of the orders that we had there. So now if I take another example, let's say, our next example is when we have a CF3 group here, we have a CCl3 group here, we have an NO2 group here, and we have a, let's say, CN group here. Again, if I have to decide the order of their acidity, then I have to compare the stability of their conjugate base. So we'll have CF3 here, CCl3 here, NO2 here, and CN here. Again, if I compare their minus I order we know that CF3 will be the most electron withdrawing, followed by CCl3, which will be more than NO2, which will be more than Cl. As CF3 happens to be the most electron withdrawing, it will help in dispersing the negative charge by inductive effect to the maximum extent, which will increase the stability of this carboxylate anion and hence will increase the stability. So again, the stability order will be this way, and so will be the order of acidity. So I hope this thing is clear now. The acidity of any acid is related with the stability of conjugate base, and stability of conjugate base is directly proportional to the electron withdrawing group, as they help in dispersing the negative charge and hence increases the stability. So does the acidity also increase. Another important comparison that most of you will be confused will be between formic acid, benzoic acid and acetic acid. So first I will compare these two cases for you. So what is written in your NCERT is, when a phenyl or a vinyl group is directly attached to the carboxylic acid, it increases the acidity contrary to expected decrease. That means they are saying that when we put a phenyl group directly attached to a carboxylic acid, we actually tend to observe, or we actually feel like that the acidity should decrease. But in reality, when in experimental they perform the experiment to find out the acidity of phenyl or vinyl substituted carboxylic acid, they found out that it actually enhances the acidity. So first we will try to understand why are we actually saying that acidity should decrease when a phenyl group is attached to the benzoic acid. So for this we again need to go back to the idea, like why carboxylic acids are acidic. So what happens is, if I write the structure of carboxylic acid, then I know the electron pairs of this oxygen are pulled by this C double bond O, due to which if I write the resonating structure, I can say it will become CO minus double bond O positive H. Due to this electron pulling by carbonyl group, I can say electron deficiency increases on this oxygen as it gets a positive charge. Since oxygen gets a positive charge, in order to neutralize its positive charge, what it does is it breaks its bond with hydrogen and takes both the bonding electrons on itself, thereby forming a neutral oxygen, and hence H plus goes out. So I can say it's the electron deficiency created by this carbonyl group which makes the hydrogen attached to oxygen more acidic. Now let's try to understand what will happen if you put a vinyl group. Let's say my vinyl group is CH2 double bond CH double bond C double bond OH. Now we know this resonance is as usual, which is going to make it more acidic. So I know CH2 double bond CH CO minus double bond O positive H. But if you observe carefully that when you are attaching a vinyl group directly to the carboxylic group, there is a resonance possible from this side also. That is, if resonance happen in this direction, then what will happen is, then the resonating structure that I will have will be CH2 plus CH double bond C O minus OH. Now in this case you can see, as this double bond is sending electrons to this carbonyl group, this carbonyl no longer is pulling electrons from this oxygen. And if carbonyl does not pull electrons from this oxygen, no electron deficiency will be created here, and then OH bond will not cleave. So I can say this resonance from the plus M effect of this vinyl group actually decreases the donating tendencies of carboxylic acid, and that is the reason why it was expected that putting a group which can do conjugation should actually decrease the acidity of carboxylic acid. But in contrary to that, what is observed is putting a vinyl or a phenyl group actually increases the acidity, and the reason given is not this resonance. The reason actually given is that when you attach a vinyl group, then the carboxylate anion is stabilized due to the inductive effect of sp2 carbons. Because we know a carbon which is sp hybridized is more electronegative than a carbon which is sp2 hybridized, which is more electronegativity than the carbon which is sp3 hybridized. So this is the electronegativity order. They say due to the presence of more number of sp2 carbon, they have more minus I effect, which in turn stabilizes the carboxylate anion and hence increases the stability. And that is the idea that we have to use for comparing the acidity of benzoic acid and acetic acid. Here acetic acid, the CH3 group is sp3 hybridized, whereas in C6H5, if I make the structure, C6H5 will be like this. And this is CH3COH. So you can say once I write its conjugate base, which will be C double bond O minus, this conjugate base is going to be stabilized by the presence of this more electronegative sp2 carbon. Since there are more number of sp2 carbon, they exert a minus I effect compared to the sp3 hybridized carbon, which actually has an electron releasing effect. And that is the reason why benzoic acid is said to be more acidic than acetic acid. Or if you go with the pK value, then we know the benzoic acid pK value is around 4.19, whereas acetic acid pK value is 4.76. And we know an acid having a lower pK value is actually more acidic, so we can say benzoic acid is more acidic. So the logic that you are going to use for comparing benzoic acid and acetic acid will be the presence of the sp2 hybridized carbon atom in the phenyl system, due to which they exert minus I effect, making it more acidic. Whereas when you compare formic acid and benzoic acid, the logic for comparison changes. Let's try to understand how. When I am comparing the formic acid with benzoic acid, again I have to compare the stability of their conjugate base. So here I can say after losing a proton, the conjugate base will be H double bond C O minus, whereas in this case the conjugate base is going to be C double bond O minus. In both the cases, the carboxylate anion is resonance stabilized. So that is the factor which is same in both of them. Whereas hydrogen, if you talk about electronic effects, there is no inductive and there is no resonance. Hydrogen as such does not show any inductive effect. Whereas when you talk about a phenyl system, I know phenyl ring as such can apply minus I and it can apply plus M also, because these electrons can be donated to the carboxylate anion. And due to this donation of electrons to the carboxylate anion, we can say phenyl also shows an electron donating effect. And if it is donating electron, we know electron donating group decreases the acidity. And that is the reason why when I am going to compare the stability of the conjugate bases, formate anion will be more stable than benzoate, and the same will be reflected in the acidity. So formic acid is more acidic than benzoic acid, which is going to be more acidic than your acetic acid. So as if you have understood, the logic for their comparison is different from the logic used for their comparison. Here it's the inductive effect of phenyl ring which dominates while comparing the acidity order, whereas here it's the resonance of phenyl ring which makes it less acidic than the formic acid. So I hope this must be clear. Again, if I compare, let's say I am having an aromatic carboxylic acid which is substituted with different groups. Let's say this has COH and there is an OMe group. I have benzoic acid as such, and then I have an NO2 group at the para position. So if I compare the type of effects, electronic effects that this group can show, then I know OMe can show minus I effect and it can show plus M effect. This is electron withdrawing effect and plus M is going to be electron releasing. And in general, if we talk about which effect dominates, then it's the plus M which dominates. So here I can see OMe will end up overall as an electron releasing group. Here a hydrogen is attached at the para position which does not show any effect, whereas if I study nitro, it shows minus I and minus M, and minus if I and minus M both effects are electron withdrawing. So I can say NO2 here will be acting as an overall electron pulling effect. Again, go back to the basic. In case of substituted carboxylic acids, the acidity will be more when an electron withdrawing group is attached. So I can say the acidity order will be one with an electron withdrawing group will be more acidic than unsubstituted, which will be more acidic than one with the electron donating group, which is also reflected in their pK values. pK value of benzoic acid, we know it's around 4.19. Whereas when you discuss one substituted with electron donating group, this pK value is around 4.46. I am telling you near pK values, whereas one with nitro group will be around 3.19. So as you can see, pK values also suggest the same order, as the stronger acid will have a lower pK value. So here we are going to end the discussion of the acidity part, but if you talk about carboxylic acid chapter, this part happens to be the most important part. So you should practice as many problems as you can on the acidity basicity questions, and in carboxylic acid chapter mainly acidity question using your general organic chemistry concept. So now we are going to move to the next type of reactions, which are reactions involving cleavage of COH bond. So in this case, the very first reaction that we will be having will be formation of anhydrides. Anhydrides will be one without water, or basically the idea is, let's say if I am having an acetic acid which is ethanoic acid. If two molecules of ethanoic acids are heated together using the dehydrating agents, which can be concentrated H2SO4, or for dehydration, that means removal of water, you can use phosphorus pentaoxide also here. So here what is going to happen is, it's going to remove a molecule of water and will cause the dehydration. That means this OH NH will leave as water, and the acids are going to join together as CH3, C double bond O, this O, C double bond O, CH3, and this will be ethanoic anhydride. Since you are forming an anhydride, or when you take carboxylic acid, this is formed by the loss of water. So you can say anhydrides are formed by the removal of water from two molecules of a carboxylic acid. So the first reaction that we have is the formation of anhydride, and the reagents that are used for dehydration is either concentrated sulfuric acid or phosphorus pentaoxide. Second reaction that we will have here will be Fischer esterification. Esterification, when done in the acidic medium, is your Fischer esterification, whereas base. So in this case, what we will do is, we will take a carboxylic acid, RCOH. We are going to treat it with an alcohol. Let's say my alcohol is HOR dash. So when an acid and an alcohol are mixed together in the presence of an acid as a catalyst, here you can use concentrated sulfuric acid as a catalyst, or you can use HCl also as the catalyst. You just need small amount of H plus to maintain the acidic medium. This is actually going to result into the formation of an ester with RC double bond O, OR dash plus H2O. Esters, as we all know, they have a fruity smell, and this fruity smell of ester is also sometimes used as a test for identification of carboxylic acid present in your reaction mixture. Because if your reaction mixture contains a carboxylic acid and if you add an alcohol to that, if you can smell some fruity, that will be due to the if you can smell a fruity smell, then it will be actually due to the formation of the ester, which confirms that acids are present there. Now this reaction is actually a reversible reaction. As I have already told you, I have already discussed the mechanism for the hydrolysis of ester to form the carboxylic acid. So the mechanism will be same. You exactly have to write the reverse mechanism from hydrolysis of ester, which is already discussed. One more thing that I want to mention here is, or which I have highlighted here is, if you see, I have written alcohol with a yellow color, and this OR dash group which I have put is actually coming from the alcohol part, and this water oxygen is actually coming from the carboxylic acid. So when an acid and an alcohol combines together, it's the OH of the acid and the hydrogen of the alcohol which leaves and forms the water, whereas it's the alkoxide part or the OR dash part in the alcohol which is present as OR dash part in the ester. So the oxygen that is present in the ester actually comes from the alcohol part. So this is your next reaction, which is reaction of alcohols with acids, which leads to the replacement of OH group of an alcohol with OR dash of the alcohol. So here I can say, if I had CH3, COH, and let's say I had an alcohol which is CH3, O18H, I am taking a heavier isotope, and I am doing this reaction in the acidic medium. Then when I want to write the ester as the product, then I know OH of acid will be replaced by OR of the ester, by OR of the alcohol, and this oxygen will be 18 oxygen plus you will get water. So this oxygen is the oxygen of the alcohol which is present in the ester. One more thing that you can see here is the rate of reaction for alcohol as well as esters will be inversely proportional to the steric crowding. That is, if I am comparing the rates of reaction of a primary alcohol and a secondary alcohol and a tertiary alcohol participating in esterification reaction, then the reaction will be fastest for primary, which will be more than primary will be faster than secondary, which will be faster than tertiary alcohol, and it will be, in case of an ester, again if I have an ester like this, if we have RCOH as the acid, then the rate of reaction for this acid will be inversely proportional to steric crowding in R. That is, what I am trying to say is, if R is a tertiary alkyl group, then the reaction will be slowest. If you replace tertiary with a secondary, reaction will become faster, and if it is primary, it will be even faster. So you should have the R part in alcohol as well as in acid, both should be sterically less bulky for a faster reaction. So these are the order of reaction. Next reaction that we are going to discuss is reaction with PCl3, PCl5 and thionyl chloride. So if a carboxylic acid reacts with any of these reagents, it actually leads to formation of acid chlorides. So these mechanisms you have already learnt in the conversion of alcohols into alkyl halides. It works exactly the same way here. For example, if I have an RCOH group here, then what you are supposed to do is, if you are using PCl5 along with it, then like in alcohols OH used to be replaced with chlorine, the same thing will happen here also, and what you will get is OH of an acid will be replaced by chlorine from PCl5. In addition to that, you will get PoCl3 plus HCl. Whereas reaction with PCl3 will also give us the same product, where your product will be 3 times of R C double bond O Cl plus H3PO3, and last will be with thionyl chloride, which will again produce RCOCl plus SO2 plus HCl. So basically it's a method of conversion of carboxylic acid to acid halides. And if you talk about which method is preferred, then it's the treatment of carboxylic acid with thionyl chloride which is preferred amongst all. Why? Because in this case separation of product is not a problem here, as the other products are gaseous, which leaves the reaction vessel and you are only left with RCOCl. So in future if you see a carboxylic acid and you are given SOCl2 along with it, you know what you are supposed to do. Just replace the OH of the acid with chlorine. For example, if I give you benzoic acid, which is pH C double bond OH, and if I say this is being treated with SOCl2, then you know I am going to form benzoyl chloride. So these reactions you should practice a number of times so that when you see a carboxylic acid being treated with a thionyl chloride, it forms the acid halide. Now I am not writing the mechanism because you might have already learned that how an OH group is converted to X using these reagents. So we'll move further, and next we are going to have is reaction with ammonia. If a carboxylic acid reacts with ammonia, it will actually lead to the formation of amide. So first what happens is, if you have a carboxylic acid and if you treat it with ammonia, so ammonia here, in addition to act as a nucleophile, we know it's also a base. So if a carboxylic acid is treated with ammonia, the first thing that happens is an acid base reaction in which it leads into the formation of ammonium salt. So first, due to acid base reaction, the carboxylic acid will react with ammonia and will form the carboxylate salt, or you can say ammonium carboxylate salt. Amide from this will only form if you heat this salt formed, that is only on strong heating you are going to get amide as the product, RCONH2 with the loss of water. So let's try to understand by an example. For example, let's say again we are taking benzoic acid. It's given that it was treated with ammonia, and on treatment with ammonia we get X, whereas X on heating gives Y. And the question is identify X and Y. We know this is an acid, this is a base. So what will happen here is, first acid base reaction will happen here, due to which it will result into the formation of carboxylate salt, which on heating will give amide. So in short, you can also remember it as, if you are having R C double bond O H, you can combine it with ammonia, which you can write it as HNH2. You are removing this water and directly combining them together as RCONH2. Now, one thing that you need to understand here is this reaction, that is reaction of carboxylic acid with ammonia, will not directly yield amides. The reaction will first, if you simply mix them together, they will form the corresponding salt, which only on strong heating will form amide, and this reaction is very important. For example, if I write one more reaction, which is, let's say I am taking phthalic acid. Now this phthalic acid is then treated with enough ammonia and we form X. This X is then strongly heated to get Y, which is then further heated to get Z, and the question is find out X, Y and Z. So X we know, since it's treated with ammonia and ammonia is, let's say it is in excess, so first thing that will happen is acid base reaction. So this acid and this ammonia will form the salt, which will be C double bond O, O minus, NH4 positive, C double bond O, O minus, NH4 positive. We know this carboxylate salt on heating will generate amide. So we can say X on heating gives Y, which is going to be C double bond O, NH2, C double bond O, NH2, which is phthalamide, which is our Y air. So what we have done is we have converted our phthalic acid into phthalamide. But what happens then when phthalamide is further heated? In this, an intramolecular reaction happens where it cyclizes to form your phthalamide, which will be C double bond O, C double bond O, NH. So this is phthalamide. So if you say this is amide and this is imide. Now no need to worry about this reaction mechanism, but this is how questions are given in your exam, because this is one of the important substrate in your Gabriel phthalamide synthesis, which you are going to learn for the preparation of amines. Sometimes they will give you phthalamide directly, and sometimes in question they will directly start from benzoic acid. So in that case you should know what will be X, what will be Y and what will be Z. So these were the reactions with ammonia where it results into the formation of amides. So the next type of reactions that we can discuss will be reactions due to carboxyl group as a whole. And in this case the first reaction that will come will be the reduction reaction. Now if I have a carboxylic acid and if I treat it with sodium borohydride, NaBH4, then sodium borohydride is a weak reducing agent which works mostly for aldehydes and ketones. So on carboxylic acid, NaBH4 is not going to have any effect, so no reaction. Whereas treatment of carboxylic acid with lithium aluminium hydride, which is taken in dry ether followed by acidification, will convert carboxylic acids into primary alcohols, CH2OH. So using lithium aluminium hydride, we can actually reduce our carboxylic acid group directly into alcohols. Or another better choice is you can use diborane as the reducing agent. Diborane as a reducing agent or BH3 as a reducing agent will again reduce it to alcohol. And if I say that carboxylic acids can be reduced using lithium aluminium hydride as well as diborane, which one is preferred? Then the method which is preferred is this, as BH3 is more selective for carboxylic acid group and it does not easily reduces other groups like esters, halo, nitro if they are present in the substrate. For example, what I am saying is, let's say if I had a substrate, let's say this is C double bond O OH and this is C double bond O ET. So this substrate, I know I am having one ester functionality and I am having one acid functionality. And let's say if I am treating them with B2H6 in a aprotic solvent, H plus water, and let's say the second one is lithium aluminium hydride in dry ether, H plus water. So what will happen here is that this reagent is more selective for carboxylic acid group. So when ester and acids are present together in the substrate, then acid will be reduced preferentially to ester and our final product you can say will have an ester intact, whereas carboxylic acid group will be reduced to alcohol. Whereas lithium aluminium hydride is more selective for ester in comparison to acid. That is, in this case what will happen is you will get carboxylic group as such, whereas ester will be reduced to alcohols. Now one thing that you must wonder right now is like, sir, just now on the previous page you said that acids can be reduced using lithium aluminium hydride also into alcohols. Then how come here you are saying that acid will not be reduced? So now to answer this question, what we need to understand is the idea of chemoselectivity. What chemoselectivity actually means. When you have a particular reducing agent, the lithium aluminium hydride can reduce ester, can reduce acid also, but the time that it will take to reduce both of them will be different based on their reactivity towards this particular reagent. So now what happens is, based on the reactivity difference, the time that they take will be actually different. For example, since it's more selective for ester, you can say that lithium aluminium hydride, if it is reducing ester in 1 hour, it may take 5 hours for the carboxylic acid, but it will get your job done even for an ester, even for an acid. So now as a synthetic chemist, what you will do is, let's say if you stop your reaction after 1 hour itself, then you know that if this was treated with this particular reagent for 1 hour, then majority of the product will be one in which ester is reduced and acid is still intact, as it takes more time for its reduction. So that is where the chemoselectivity comes, and that is where we cannot give you a hardcore list for the reducing agent, because it depends from the conditions to conditions in which question is framed. When I am giving you a carboxylic acid and I am giving you a lithium aluminium hydride, that means I do not care how much time is taken. I want to reduce carboxylic acid with the lithium aluminium hydride. So then I want to do that reaction and lithium aluminium hydride will reduce carboxylic acid. But when both of them are present together in the same substrate, now you need to understand what examiner is trying to ask you. He is trying to ask you the difference in the reactivity of these groups towards these reagents, which makes them selective in nature. So yes, lithium aluminium hydride reduces a carboxylic acid also, it reduces an ester also. But when both of them are present together, you will understand that which is more reactive towards lithium aluminium hydride. That is the overall idea here, that okay, if you are using this set of reagents, then if ester and acids are present together in the substrate, then esters will be reduced with lithium aluminium hydride, whereas a more selective reagent for the reduction of carboxylic acid group is diborane. So this was your reduction reaction. Next reaction that we can have is, which is due to COH group, will be decarboxylation. Now this decarboxylation reactions, majority of them you have learned here and there in other chapters, out of which I will write the first one, which is going to be soda lime decarboxylation, which you have learnt in the hydrocarbon chapter for the preparation of alkanes. So in this case, what happens is, when you have a sodium salt of carboxylic acid, sodium or potassium salt of carboxylic acid, and when it is treated with a mixture of sodium hydroxide is to calcium oxide taken in the ratio 3:1, then what happens is, it undergoes decarboxylation to form the corresponding alkane with one carbon less. So this I am telling you so that in future, if you have, let's say someone says soda lime decarboxylation, you should know the reactant. What is the reactant here? What is the reagent used? What is the final product? After recollecting these many things about a reaction, then only we will write, because first we need to have the entire framework in our mind. So if I say what exactly happens in this reaction from the mechanism and everything point of view, you can say, let's say I am having a carboxylate salt, which can be sodium or potassium. When you treat it with this NaOH is to calcium oxide mixture and you heat it, what happens is, this on heating undergoes decarboxylation, which you can represent as this. So what happens? A double bond forms between carbon and oxygen, so this leaves as CO2, and it leads to the formation of R carrying a negative charge. R will be the alkyl part, so we can say carbanion is the intermediate formed in the soda lime decarboxylation, and this R minus then can be protonated with any proton source present in the solution, or you can add a bit of acid from outside. So this R minus will be protonated for your hydrocarbon. If you see, one carbon has left as CO2, so I can say if number of carbon atoms in my sodium salt was N, here the number of carbon atoms are going to be equal to N minus 1, as one has already left as CO2. Now this CO2, since the medium is basic, you can say along with this you will get sodium carbonate, as sodium hydroxide and CO2 will form sodium carbonate. In this reaction, the point that you have to notice here is rate of decarboxylation is directly proportional to the stability of carbanion, as the formation of carbanion is said to be the rate determining step. And if you talk about the stability of a carbanion, we know it is directly proportional to electron withdrawing groups, or the stability of a carbanion will be inversely proportional to electron donating group. Electron withdrawing group will show -I, -H and -M effects, whereas electron donating groups will show +I, +H and +M. So you can say if you are decarboxylating a carboxylic acid which is having electron donating group, its rate of decarboxylation will be slower than when it is having electron withdrawing groups attached to itself. So let's take it with an example. Let's say if I am having CH3, CH2, C double bond, O minus, Na positive, and I am heating it with soda lime mixture, NaOH, calcium oxide, then what will happen is this is first going to undergo decarboxylation. So here formation of carbocation you can say as the rate determining step. So CH3 CH2 minus, this can be protonated from any solvent present and you will get CH3 CH3. So if you see, the number of carbon atoms here are 2, whereas the substrate with which you started here, the number of carbon atoms are actually 3. So in this case we get an alkane having a carbon less than the starting material. If you want to compare the rates of decarboxylation, then you can compare it as like this. If I am having CH3, COH, CH3, CH2COH, CH3, C, CH3, H, COH, and if I am having CH3, 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 COH. So as this is the most electron donating group here, the rate of decarboxylation will be in this manner. All you can do is, after decarboxylation, the carbon ions that will be formed will be CH3 minus, CH3 CH2 minus, here it will be CH3 CH, CH3 minus, and here it will be CH3 C, CH3, CH3 minus. Here if you are talking about the stabilities of carbon ion, primary carbon ion will be less stable than this is methyl, this is primary carbon ion, this is secondary, and this is tertiary. From your general organic chemistry, the order of stability of carbon ion will be this, and so will be the order of decarboxylation, as order of decarboxylation will depend on the stabilities of carbon ion. So this is one, decarboxylation. Second one that we can discuss is, or which we have also discussed, is in the call-base electrolysis. In this case, what happens is, when you have a sodium or potassium salt of carboxylic acid, and when you electrolyze it, then we get a hydrocarbon containing twice the number of carbon atoms present in alkyl part of salt. That is, what I am trying to tell you here is, let's say if I am taking the sodium or the potassium salt of carboxylate anion as, let's say, sodium acetate. This, if I am doing its electrolysis, then what I am saying is, this will be the alkyl part that is attached to this carboxylic as salt. So what will happen is, we are going to get an hydrocarbon. In this, if it contains one carbon, our hydrocarbon will contain 2 carbon atoms. So this is the overall thing that happens along with the CO2 gases eliminated here. So let me just try to give you a little insight into the mechanism how it happens is, you know, when you are having sodium acetate, it is an electrolyte. Electrolyte, when you pass electricity through its solution, it will dissociate into its ions. So when you have dissociated it into its ions, the ions are going to migrate towards the electrodes which are oppositely charged. Anode is an electrode which is positively charged in electrolytic cell, and this is the electrode where oxidation happens. So out of them, the one which is negatively charged will move towards positively charged electrode, and this CH3CO minus is going to undergo oxidation by the loss of electron. Now after the loss of electron, one electron will be left unpaired on oxygen. So what is going to happen from here is, this O radical is going to donate its electron to this carbon and will ask this carbon to make a bond. But for this carbon to make a bond, it needs one unpaired electron. We know in this bond there are two unpaired electrons. So to make a bond with that oxygen, what it will do is, it will take away this electron and share it with oxygen, and will ask the alkyl part to go away. So if this bond is cleaved homolytically, what will happen is, you will create CH3 radical, plus it will result into the formation of CO2. So you can say why this reaction happens, because CO2 leaving is the driving force. So this CH3 radical, which is produced from one molecule, like this there will be many molecules undergoing oxidation at anode. So you will be having many CH3 radicals which are going to combine with each other to have your C2H6, or the formation of ethane molecule. So this is Kolbe's electrolysis. I have only written reaction at anode. You cathode also you can write, where water actually gets reduced. So that part you can just study it from your hydrocarbon chapter, as Kolbe's electrolysis comes there. Another reaction which is not there in your NCERT will be the Hunsdiecker Borodin reaction. In this case, this is also an example of decarboxylation reaction, where what happens is, silver salt of carboxylic acid on treatment with bromine, on treatment with X2, here X2 can be bromine or chlorine in carbon tetrachloride, leads to formation of alkyl halides with one carbon less than the parent salt. That is, what I am trying to tell you here is that if I take a silver salt of any carboxylic acid, let's say I am taking this COOH, this if I am treating it with X2, which can be chlorine or bromine, in organic solvent, let's say CCl4, then what will happen is, this part will undergo decarboxylation. So that will leave as CO2, plus you will result into the formation of an alkyl halide with an halogen attached to where this carboxylate group was attached. So all you have to do is remove this CO group as CO2 and put a halogen here. This halogen can be chlorine or bromine, anything. So this is the salt, this is the halogen. Now there is one point here, that the yields of alkyl halide is actually in the order. Primary alkyl halides are formed in larger yield, which will be formed. Primary is formed more than secondary, which is formed in more amounts than tertiary alkyl halides. One more reaction is there, which is when iodine is used as the halogen. When iodine is used as the halogen, then salt is to iodine ratio is very important. That is, when they are taken in the ratio 1:1, then as usual you will get your alkyl halide as the major product. Whereas if you are taking salt is to halogen in the ratio 2:1, then in that case ester will be the major product, and in that case the name of the reaction will be Simonini reaction. So while doing it with iodine, you have to be very careful with the salt is to iodine composition. If it is 1:1, it will work as normal Hunsaker-Borodin reaction, whereas if you mess up with the ratio, you can take it as 2:1, then instead of getting alkyl halide as the product, you are going to end up with ester. So I am going to just give you a little insight into the mechanism of this reaction. How it happens is, first of all, if I have a carboxylic acid RCOH, this you can treat it with silver hydroxide, which acts as a base. So this will lead to the formation of carboxylate salt of silver, which will be O minus Ag plus, and here water will go. So here this carboxylate salt can react with, let's say I am taking halogen as bromine. So this minus will attack this Br, breaking the Br-Br bond. So this Ag plus can go with that Br minus. So this will be AgBr, and you will have Rc double bond O Br. Now this R O Br bond is not very strong, so on little heating this undergoes homolytic cleavage. We know on homolytic cleavage what happens is you form radicals. So this carboxylate radical, you have seen in Kolbe's electrolysis how it used to break its bond with the alkyl part and will leave as R radical. So here CO2 will leave. So this R radical which is formed can attack another molecule of bromine. It can offer this bromine 1 electron. So this bond will also break homolytically, resulting into the formation of RBr. If you can think of ester as a byproduct, how ester will be formed? Let's say you have R radical present in the solution, plus you have some of this carboxylate radical also present. So if you combine this carboxylate radical with R, you will actually end up into the formation of RCOR, and that is how you can explain ester as the byproduct, which will happen in case of iodine when you are using it in the ratio 2:1. So this was your Hunsaker-Borodin reaction. So next we can do is reactions due to substituent present. So in this category, the first one that we will have is the reaction which is used for alpha halogenation of carboxylic acid. So in this case what happens is, let's say if I am having CH3COH, and this is then treated with red phosphorus taken along with a halogen. Let's say X2 is Cl2 or Br2. You are taking red phosphorus followed by hydrolysis. Let's say you are adding water. So it will result into the replacement of this carbon will be known as alpha carbon, and the hydrogens attached here will be will be alpha hydrogens. So what will happen is halogenation is going to happen only at this alpha position. So what will happen? We can replace one of the hydrogen with a halogen and you will get alpha halo acid. If you again repeat HVZ, you can actually replace one more halogen or one more hydrogen also. Then you will get dihalo at the alpha position. And if you do it one more time, then you can actually replace all the alpha hydrogens present next to this carboxylic acid. So now we will actually see how this reaction goes. So when you are taking X2 along with red phosphorus, you can actually assume that it will result into the formation of PX3. This PX3, let's say, is our PCl3. So what is going to happen here is, when I am taking CH3C double bond OH and it is treated with X2, or let's say X2 here is Cl2 in the presence of red phosphorus, and if I believe that they will form PCl3, then what will happen here is, we know PCl3 is actually going to convert this OH into Cl. So first my acid will be converted into the acid halide. This acid halide is then going to tautomerize. If it tautomerize, then you know how tautomerization happens. I can write this thing as CH2H, and a hydrogen from this position will move on to oxygen. So this can be written as CH2 double bond C OH and Cl. Now I know enolic forms are actually nucleophilic. So what will happen is, if I have a molecule of Cl2, then this electron pair will come back and this electron will move on carbon, or you can say the electron from the pi bond will actually be donated to one of the chlorines and this bond will break. So what you can say here is CH2 Cl C double bond O positive HCl. You can remove this hydrogen as H positive to give you the neutral product, which will be CH2 Cl C double bond O Cl. So if you see that you have put a halogen onto the alpha position and the hydrogen has been replaced by chlorine, and this is where the last step, second one, comes, which is actually the hydrolysis of acid chloride. We know since acid chloride is the derivative of carboxylic acid, on hydrolysis it should produce carboxylic acid. So hydrolysis will convert COCl group into C double bond OH, and this will become CH2Cl. You can do monochlorination, you can do dichlorination, you can do trichlorination, depending on how many hydrogen atoms are present onto the alpha position. So one last reaction that is there in this category is your ring substitution. In this case we will have aromatic carboxylic acid. So in this case we know that benzene is capable of undergoing electrophilic aromatic substitution. So let's say when you have a substituted carboxylic, a benzene ring which is substituted by COH, then we know COH group is electron withdrawing group. So it deactivates the ring towards electrophilic aromatic substitution. That is, if you have benzene and if you have benzoic acid, if I ask which one of the following will be more reactive towards electrophilic aromatic substitution, then the answer will be benzene, as benzoic acid has a COH group which is ring deactivating group, which decreases electron density on the ring and hence decreases the rate of electrophilic aromatic substitution reactions also, and it is a meta directing group. What does this meta directing group means? If you look into the position of this benzene ring system, then the position on which the carboxylic acid group is directly attached, that position is known as ipso. Position next to ipso is known as ortho. Position next to ortho is meta, and position next to meta will be para. That is, ortho is with respect to benzoic acid, it is 1, 2, meta is 1, 3, and para is 1, 4. That means for this benzoic acid system, if I take a nitrating mixture, for example, if I take concentrated sulfuric acid plus concentrated nitric acid, which I know is a mixture used for nitration, then what will happen here is this mixture actually generates NO2 positive as an electrophile. And if this electrophile is supposed to go into the benzene ring, then due to deactivating nature of COH, it's a meta directing group. That means this NO2 will go at meta position. So the product will be COH and NO2 at meta position. So you can say the final product will be meta nitro benzoic acid. Now, in addition to this, we know one very famous reaction for electrophilic aromatic substitution reaction is Friedel-Crafts reaction. And if you know about Friedel-Crafts reaction, Friedel-Crafts reactions are not shown by those benzene rings which has only electron withdrawing group present on it, or that electron withdrawing group has to be highly deactivating. So basically, when the benzene system is too much electron deficient, then Friedel-Crafts reaction actually does not happen. For example, I can say if I am trying to do Friedel-Crafts reaction for benzoic acid, nitrobenzene, then in these cases there will be no Friedel-Crafts reaction, as these electron withdrawing groups deactivates the benzene ring to a very large extent and they become very less reactive. Or you can say in benzoic acid what more happens is, let's say if this is COH and if this is benzene ring, then this carboxylic group we know deactivates, but this carboxylic acid sometimes combines with AlCl3 and it becomes further more deactivating, which again limits its use as a substrate in Friedel-Crafts reaction. So you have to be careful, the rings which contains only electron withdrawing group does not undergo Friedel-Crafts reaction. An example of such reactions will be your benzoic acid and nitrobenzene. So next what we have is heating effects. Now these things are not directly given in your NCERT, but we'll cover it as an extra stuff. So when you talk about heating effects on monocarboxylic acids, so in this case what happens is, let's say if I have a carboxylic acid which contains only one COH group, then I know monocarboxylic acids on heating will undergo dehydration to form the corresponding anhydride. So you need to remember that monocarboxylic acids on heating will undergo dehydration, where two molecules of the same acid will combine to form the corresponding anhydride. For example, next time if I ask, you are having an acetic acid and you are heating it. On heating, it should lose a molecule of water and it should form ethanoic anhydride. This is a reaction for which you had used earlier concentrated sulfuric acid or P2O5. So this is something that we already know. Next, we are going to move on to the heating effects on dicarboxylic acids. If you recollect, in the beginning I told you the series of dicarboxylic acids, and here we are going to discuss all of them. So the first one will be on oxalic acid. What happens to oxalic acid when you heat it? For example, if I am having COH and COH, this is oxalic acid. So this on heating first gives formic acid HCOH plus CO2. So here it gives formic acid plus carbon monoxide first, but if you continue, so oxalic acid on heating will first give you formic acid plus carbon dioxide, which on further heating will give H2O plus CO gas. So this is the heating effect on oxalic acid. Next we will have is malonic acid. If you recollect what is malonic acid, this will be an example of 1,3 diacid. Now this becomes important because when the acids will be having 1,3 relation, then they are going to decarboxylate readily. So next is malonic acid, which will be a 1,3 acid. So let me write it as CH2, C double bond OH, C double bond OH. So what will happen in this case is, if you are heating it, then 1,3 acid in the sense, if you number this carbon as 1, then the other carboxylic part will get the third number. So 1, 2, 3. So this on heating is actually going to decarboxylate and will give you acetic acid plus CO2. So how it decarboxylates we can understand from this is one example. Whenever you are having 1,3 acid, what you are going to do is you are going to remove one of the carboxylic group as CO2, remove this CO2 and directly attach H there. The mechanism of this decarboxylation can be understood in terms of beta keto acid. Beta keto acids also readily decarboxylates on heating. For example, if I am having a substrate like this, which is CH3 C double bond O, CH2 C OH double bond O. So if I say the position right next to carboxylic group is alpha, this will be beta. So since I have a keto group at beta position, this is a beta keto acid. So what happens in this case is, on heating, the reaction actually passes through a 6-membered transition state. In that, what happens is, this hydrogen donate its electron in between this carbon and oxygen. When this bond will move here, carbon will exceed tetravalency, due to which it donate its electron for this carbon-carbon bond. Again, when this bond will move here, this carbonyl carbon will exceed tetravalency, so this bond moves in between oxygen and hydrogen. And all the three are happening simultaneously. So you can say this is 1, 2, 3. When this will be donated here, this bond will break, shift in between these two, and this will be shifted there. So what I can say is, if I write this transition state, then you can say it is CH3, C, O, CH2, C double bond O, and there is H. So how I am going to represent it as, I am going to represent the new bonds formed and the new bonds formed and the old bond breaking by dotted lines. So I can say this hydrogen starts cleaving its bond with this oxygen. So I am showing it with the dotted line. Where is this bond moving? This is actually moving in between carbon and oxygen. When this bond moves in between carbon and oxygen, this bond starts to break. And when this bond starts to break, it develops a partial double bond character into this bond. When this bond develops a partial double bond character, this CO bond breaks and it tries to shift in between oxygen and hydrogen. So that is the 6-member transition state which forms. So finally, when all the bonds are broken and formed completely, what you are going to get is CH3, C, OH, double bond, CH2, plus CO2. So after decarboxylation, if you see that the COO part of the carboxylic group has left in the form of CO2, and it results into the formation of enol. We know enol forms are less stable, so this will tautomerize back to your keto form. So you can write it as CH3, C double bond O, CH3. So as I said earlier, in the decarboxylations also, if you are having something like this, for decarboxylation what you are supposed to do is, you are just supposed to eliminate this CO2 part and connect this hydrogen here. So that will be CH3, C double bond O, CH3, which gives that as the product. So this is the mechanism of decarboxylation, which happens easily in case of 1,3-diacid. It happens easily in case of beta keto acid. Plus I'll give you a list of other substrates where it happens very easily, and that will be, so what we have seen is it happens easily in case of beta keto acid, if this carbonyl group is not present, and let's say if you are having a nitro group present there, then also decarboxylation will happen easily. If you are not having if you have alpha cyano group, in that case also it will decarboxylate easily. If you are having CH2, C double bond, CH2, COH, this is alpha, beta, gamma. So this is beta, gamma unsaturated carboxylic acid. So all these substrates are examples. In addition to this, you are having COH, CH2, COH. So if the two acids are in 1,3 relation, then also they will readily decarboxylate. So in all these examples, this CO2 group is going to leave the molecule, and mechanism I have told you how to write. So this is the heating effects on malonic acid, which was 1,3 acid, and if you are not having 1,3 acid, let's say there is something else present on the third position, it can be a keto group, it can be a nitro group, it can be a CN group, it can be a double bond, they can also undergo decarboxylation readily on heating. Next will be, after malonic, you will be having succinic acid. In case of succinic acid, what will happen is, you are having COH and you are having COH. In this case, when it is 1, 2, 3, 4, now the relation between two carboxylate group is 4, or they are separated by 2 carbons. In this case, they are actually not going to decarboxylate, rather it is going to undergo dehydration to form cyclic anhydride. So it will be CH3. So this will be the cyclic anhydride formed. So when 2 carboxylic acids groups at a distance of 1 and 4, then they cyclizes to form the anhydride. Same thing will happen in case of glutaric acid also. In glutaric acid, the 2 carboxylic group will be at what positions? 1, 5. So in this case also, 1, 5 will also undergo dehydration to form the cyclic anhydride. So this happens in case of 1, 4 and 1, 5. 1, 3 you have seen decarboxylation, 1, 4 and 1, 5 undergoes dehydration to form the cyclic anhydride. Whereas when we will go with 1, 6, which will be adipic acid. In case of adipic acid, they will be separated by how many carbons? 5. So here they are separated by 3 carbons. So in adipic acid, they will be separated by 4 carbons. So if I am making one COH group here, so this will be 1, 2, 3, 4, 5, and there will be one more COH. So if 2 carboxylic acids are at a distance of 1, 6 position, then what they will do is they cannot cyclize to form the anhydride, as anhydride will be 7-member ring, and we know 7-member rings are not stable. So what they do is they cyclizes to form ketone with 1 carbon less. That is, how many carbons are there? There are total 6 carbons. So this is going to decarboxylate. It will remove one CO2 and it will actually form a cyclic ketone which will have 1 carbon less than the parent acid. So if you get a 1,6-diacid and if you are heating it, you will get a ketone with 1 carbon less. Similarly, if I have pimelic acid, which will be a 1,7 acid, this will also on heating cyclizes to form a ketone with 1 carbon less. So this is the heating effects on dicarboxylic acids. We have discussed what happens to oxalic, malonic, succinic, glutaric, adipic and pimelic. Next will be on hydroxy acids. Now hydroxy acids are of many types. The first one, let's say it is alpha hydroxy acids. In case of alpha hydroxy acids, let's say I'm having CH2, OH, C double bond, OH. Alpha hydroxy acids on heating forms lactites. Now how this lactites look is actually, if I make structure as this, C double bond, OH, this is 1 because alpha position you are having an OH group, and then similarly you can make another one as OH, C double bond, CH2, OH. Then all you need to do is remove water molecules. How? Remove one OH and H from here, and similarly remove one OH and H from here. So what you are going to get? It will be C double bond, 1 oxygen here and 1 oxygen here. This will be CH2, C double bond, this thing. So this will be your lactite. So alpha hydroxy acids on heating forms lactites. Let's go to beta hydroxy acids. What happens on heating to beta hydroxy acids? Then it will be CH2, OH, CH2, COH. So this is alpha position, this is beta position. So what happens here is it actually undergoes removal of water from alpha and beta position. So what forms here is alpha beta unsaturated carboxylic acid. So beta hydroxy acids on heating will form alpha beta unsaturated carboxylic acid. If we are having gamma hydroxy acid, then they will actually result into the formation of cyclic esters which are known as lactones. So this is alpha, this will be beta, this will be the gamma carbon and OH. So if I am heating a gamma hydroxy acids, then it is again going to remove it as OH and H, and you will result into the formation of a cyclic ester. This is alpha, this will be beta, this is a gamma, gamma carbon has an O which will be now attached to carboxylic group. Similarly, if I am having alpha, beta, gamma, delta hydroxy acid, delta hydroxy acids also forms cyclic esters which are known as lactone. So this will be like C double bond OH. So this is alpha, this will be beta, this will be gamma, this will be delta, and this will be OH. So you have to remove OH and H. It's like acid and alcohol reacting together, and they will result into the formation of ester, and cyclic esters are known as lactones. So this was something extra that was not there in your NCERT. Other than this, what we can discuss is, now carboxylic acid derivatives are not given as such into the carboxylic acid part. So I am not going to discuss it, but the carboxylic acid derivatives part you have seen it here and there in others chapter. For example, if I talk about RCOCl, you have seen it into the aldehyde ketone chapter where you did Rosenmund reduction for its preparation as an aldehyde. RCOCl on Rosenmund reduction will give you aldehyde. In amines chapter you will meet amide, where amides will form amines using Hofmann-Boramide reaction. So those reactions I am avoiding here, as you will learn it in the other chapter. What you will not learn in the other chapter is typical reaction of carboxylic acid derivatives. Like what type of reaction carboxylic acid derivatives show, and what is the order of reactivity. So in this case, the type of reactions that they show is actually a nucleophilic acyl substitution reaction. Now what is an nucleophilic acyl substitution reaction is that if I am having a carboxylic acid derivatives as RCOL, where this L can be halogen. If it is halogen or mainly chlorine, this will be an acid halide. If this L is my OCOR, then this acid derivative will be my anhydride. If this L is my OR group, or let's say OR dash, then this will be ester. And when that is NH2 group, when L is NH2 group, it will be amide. So let's say if I have a carboxylic acid derivative which I am representing it as RCOL, where L happens to be the leaving group, where L I can say is also the leaving group. So if this undergoes attack by a nucleophile, Then you know nucleophile is an electron rich species which prefers to attack the center where you have maximum positive charge. So I know this nucleophile will prefer to attack at this center and will try to replace this L. So let's say L gets replaced and you get RC double bond O Nu plus L minus. So this reaction is an example of nucleophilic acyl substitution where a nucleophile attacked this RCOL or your carboxylic acid derivative and it replaced the L group present. So now for the above reaction to be successful, the most important condition is that the incoming nucleophile must be a stronger base, than L which is present in the acid derivative. Why are we saying this? We'll try to understand, but the main reason is as bad base is a good leaving group. So this you will understand only if when you actually know how this mechanism is happening. But what I am telling you here is for this reaction to be a successful reaction, the condition is that this nucleophile must be a stronger base than the leaving group which has left. Then only this reaction will happen, otherwise there will be no substitution. That is, if nucleophile will be a weaker base than L what is already present, then you cannot expect the replacement of that L present in the carboxylic acid derivative. So let's see, why am I saying this is? Let's try to understand the mechanism. So when you look into the mechanism, the first step, which is also the rate determining step, is actually the attack of the nucleophile on the carbonyl carbon. So this carries a delta positive. So I can say this nucleophile will come and attack here, and since carbon has to maintain tetravalency, this bond will move up. So RDS, or you can say RCO minus L, and you have a nucleophile. This intermediate, if you see, the hybridization of the carbon atom has changed and it's a tetrahedral intermediate, and this tetrahedral intermediate is unstable. As you can see, the crowding has increased around the carbon. So what will happen is this O minus will come back and will form again the pi bond. Then there are two possibilities, that if L leaves, that is when this is coming back, one of them has to break the bond with the carbon, and let's say that happens to be RCO Nu, and when L will go, it will go as L minus. Or there is a possibility that when this has come back, the Nu can break its bond, and then if nucleophile leaves, then the product will be R C double bond O L plus Nu minus. So this is what I was trying to tell you here is, who is going to leave from here will be actually depending on who is a good leaving group, and a good leaving group will happen to be a bad base. That is, if L leaves, then it means L is weaker base, as weaker bases are good leaving group. Whereas if from this tetrahedral intermediate, if Nu itself leaves, that means the Nu minus is a weaker base. You just see Nu minus is actually the attacking reagent. When the attacking reagent is a weaker base, then if you compare the reactants and the product, you will say RCOCl is again RCOCl and there has no reaction happened here. That means when the incoming nucleophile is a bad base compared to the R, then it will not result into the substitution reaction, because from the tetrahedral intermediate, when it will come that who is going to break its bond, then your nucleophile will break its bond because it will be a weaker base. That is, for this reaction to be a successful reaction, there is only possibility when you want to replace this L with the nucleophile, condition is L has to be a weaker base or the nucleophile that is coming should be a stronger base. Then only from this tetrahedral intermediate, when one of them has to break its bond, for replacement to happen you want L to break its bond, and that will only happen when L is a weaker base than Nu minus. So this is one of the most important criteria. This is an acyl group. RCO group is known as acyl group. You are trying to replace the L attached to this acyl group with a nucleophile. That is why we are calling it as nucleophilic acyl substitution. So if you want this L group to be replaced by this nucleophile, one of the most important condition is it has to be a stronger base than this L, otherwise it will result into no reaction. Another few criteria is that this carbonyl carbon should be enough electrophilic to undergo attack by this nucleophile, or this nucleophile should be strong enough to attack on the carbonyl center. In addition to nucleophile being a stronger base, another criteria is that this carbon should be enough electrophilic and this nucleophile should also be enough nucleophilic. So one last thing that we will discuss is the order of reactivity. Of different carboxylic acid derivative towards nucleophilic substitution reaction. So let's say I have RCOCl, which is acid halide. Then let's say I'm having RC double bond O, C double bond O, R. This will be anhydride. Then next will be RC double bond OR dash, this is my ester, RC double bond O NH2. Let's say this is my amide, and I am comparing their reactivity towards nucleophilic acyl substitution, and I know that a good leaving group favors nucleophilic acyl substitution. If you can identify who all are the leaving groups, then in this case this Cl minus will be the leaving group. So leaving group here will be Cl minus. If you compare the anhydride with RCOCl structure, this part will be the leaving group, that is O minus CO R, and if you consider here, it will be the O minus or R dash O minus part which will be the leaving group, and in this case it will be NH2 minus. So if I compare the leaving group ability of these species, I can say who can undergo replacement by a nucleophile faster. How we can do that? I know the one which will be a weaker base here is going to be the good leaving group. So for that I write their corresponding acid. Let's say if I write the acid or the conjugate acid of this base, that will be HCl. If I write the corresponding acid of RCO minus, it will be OHCOR or RCOH. This will become HO R dash and this will become ammonia. If I write their pK values of these acids, then the pK value of HCl we know it's around -7. Carboxylic acid has nearly pK values around 5. Alcohols will have pK values around 16 and NH3 has pK value around 33. And we know the one which has the lower pK value is actually the stronger acid. So if I compare the acidic strength, I can say HCl is the strongest acid, then carboxylic acid, then alcohol, and then ammonia. If this is the order of acidity, then I can say their conjugate base, which will be Cl minus, O minus, COR, R dash O minus, and NH2 minus. If I go with the Bronsted-Lowry acid base concept, if the acid is stronger, conjugate base will be weaker. So I can say here the strongest conjugate base will be of the weakest acid. I can say NH2 minus is the strongest base, followed by R dash O minus, followed by O minus COR, and then Cl minus. So Cl minus happens to be the weakest conjugate base, or I can say since it's the weakest base, it's going to be the strongest leaving group or the better leaving group. That is why the leaving group ability will be Cl minus will be more than O minus COR, which will be greater than R dash O minus, which will be greater than NH2 minus. Better the leaving group, faster the nucleophilic acyl substitution. So you can say acid halides are more reactive than anhydrides, which are more reactive than esters, and which are more reactive than amides towards nucleophilic acyl substitution. This is one way to look at these substrates with respect to the leaving group tendency. Again, if you see the reactivity of all these carbonyl compounds towards the nucleophile is actually due to the presence of the positive charge on this carbonyl carbon. So I can say if intensity of positive charge is more on this carbonyl carbon, the rate of reaction will be faster. So if I write RC double bond OCl, then as a substituent, this chlorine will have largely inductive effect. There is already a positive charge on this carbon because oxygen is polarizing the pi electron density towards itself, and chlorine will also put slight positive charge due to its inductive effect. As we know, for halogens, inductive effect is a major effect. Then comes the acid anhydride. Now there is a single oxygen. This is delta positive, this is delta positive. Now this oxygen will try to decrease electron density at these carbonyl center by plus m effect, but since one oxygen is giving it at two places, the donation is not effective, and minus I of oxygen is also there, which makes anhydrides a bit more reactive than esters, because in esters we know the positive charge that this oxygen is going to put on the carbonyl carbon will be neutralized by positive charge, will be neutralized by plus m effect of oxygen. So we can say the positive charge which oxygen puts on this carbon is actually neutralized by the O of the alkoxide part, which decreases the positive charge density, and hence it decreases the electrophilicity of the carbonyl carbon, which is actually responsible for its lower rate. And the same happens in case of amide. Again, the oxygen will polarize the bonds toward itself, creating a positive charge, which will be diminished by the electron donation of NH2. As nitrogen is a better donor than oxygen, if I am considering their plus m effect, then nitrogen, because of its Less electronegativity is a better donor than oxygen, so it will neutralize the positive charge more. Positive charge density will decrease more, and hence the reactivity. So this, based on electronic effects also, you can explain which is more reactive and which is less reactive. So if I compare the reactivities of aldehydes ketones with carboxylic acid derivatives towards a nucleophile, then the overall order will be acid halides are the most reactive, followed by anhydrides. After this, the next reactivity will be for an aldehyde, then ketone, then your ester, and the last one will be amides. After amides, if you want to write, you can write a carboxylate anion. If you are not considering carboxylate anion, then you can say amide is the least reactive carboxylic acid derivative, or acid halide is the most reactive carboxylic acid derivative towards a nucleophile. So this is where the theory part we will finish, and when we will start problems, we will consider additional concepts whichever will come during the discussion of the questions.